Today we shall be discussing on the characteristic of gradually varied flow. Well, in the last class we have discussed how we can classify gradually varied flow, and then we just started discussion on characteristic of gradually varied flow. Well, before going to characteristic of gradually varied flow, let us summarize what we did in our last class so that we can go in a more convincing way to the characteristic of gradually varied flow. Well, in the last class we started with the classification of gradually varied flow. Well, and we could see that how we classify the gradually varied flow. First, for classifying gradually varied flow, we do it on the basis of the slope on which the flow is occurring, and then we divided the zone, the flow zone above the bed into three different zones, zone 1, zone 2 and zone 3, and based on the zone on which this particular flow is occurring, based on that we classify. That means we classify on the basis of slope as well as on the zone. So, slope means again there were different type of slope. Say it can be mild slope. Mild slope means when the bed slope is less than critical slope. Well, and then it can be steep slope, means the slope is steeper than critical slope, and then again critical slope. Of course, critical slope means when the uniform flow occur for a particular discharge in that particular section, that particular channel, uniform flow occur at critical depth. So, that particular slope we call as a critical slope. And then of course, we got that flow can be there, gradually varied flow can be there over a horizontal bed also. So, and then over adverse slope, say slope is in negative direction. Negative direction means slope is, bed slope is not falling in the direction of flow, rather it is rising in the direction of flow. So, that sort of slope we referred as adverse slope. So, in that process again zone 1, zone 2, zone 3 are always there, that we did discuss elaborately in the last class. So, by that process we could classify the channel, we could classify the gradually varied flow profile into 12 different classes and 12 different type, that you can see that these were M1, M2, M3, then it was S1, S2, S3, and then we had for critical slope we have C1 and C2. And why C, well sorry, here it should be C3. We had C1 and C3, and why the C2 is not existing? Because the zone 2 is not existing in case of critical slope, because normal depth line and critical depth line coincide in case of critical slope. So, that zone itself is not existing. So, the profiles are C1 and C3. Then in case of horizontal slope we got horizontal bed, rather we got H2 and H3. Here H1 is not existing because the depth of uniform flow in case of horizontal slope is at infinity. So, we do not have the zone 1 which cannot be there beyond infinity. Well, so that way we had only H2 and H3 profile. And similarly, in adverse slope we had again A2 and A3 profile. Here also A1 is not existing. The reason is that the uniform flow depth in case of adverse slope is imaginary. So, we cannot have anything when we do not know about the exact location of yn, it is an imaginary depth. So, beyond this we cannot have any other zone. So, that way we do not have the A1 profile, right. So, we had A2 and A3 profile, and these are the 12 different types of gradually varied flow profile that can occur in nature. And of course, these profiles, if the slope in the nature keep on changing, definitely it will keep on changing when a river is flowing. Then we can get combination of different type of flow profile, and that combined profile actually give us the water surface profile in a natural channel. Well, with that we can now go on to the characteristic of gradually varied flow. Well, you can concentrate into the slide that we have derived the governing equation already. That governing equation is dy dx is equal to, that can be expressed in this form, SB, then 1 minus SF by SB, then 1 minus q square T by GA cube. So, this way the governing equation we could derive. Of course, it has different form, and as we explained in the last class, for analyzing characteristic of different types of profile, we can have this form in a more simpler way, and in terms of the normal depth of flow, critical depth of flow, and the depth of gradually varied flow at any section. So, and that we can achieve by considering the channel to be wide rectangular channel, and we did discuss in the last class that governing equation for wide rectangular channel, using Chase's equation as resistance formula, we could get the equation in this form, that is dy dx is equal to SB into 1 minus yn by y whole cube divided by 1 minus yc by y whole cube, where yc is the critical depth, yn is the normal depth, and y is depth at any section within the gradually varied flow portion actual water surface depth. So, that way and SB is the bed slope, SB is the bed slope. Well, and starting from this equation, now we can see how the characteristic of M1 profile can be determined. Of course, if we just think what we did in the last class, we could at least establish that M1 profile is a rising profile, that we have already established. Okay. And well, just to recall that, say dy dx is equal to SB into 1 minus yn by y whole cube divided by 1 minus yc by y whole cube. Well, that is the equation, and in case of mild profile, that is mild slope, our CDL line is here, NDL line is here. Well, so it means that critical depth is this one yc, normal depth is yn, and suppose profile is here in zone 1 because it is M1, so it is in zone 1. So, depth at any section is say y, and as such we get that y is greater than yn, that is the normal depth at any section of the gradually varied flow portion, and yn is greater than yc. So, that we could get. And then if it is like that, that means this ratio yn by y, this is becoming fraction, yn is smaller than y. So, this is becoming fraction, cube of the fraction is definitely less than 1, 1 minus something less than 1 is positive. Here also yc by y being greater than yc, this is also a fraction, and that cube of the fraction will be definitely a fraction, and 1 minus something less than 1, which is a fraction. So, that is also therefore positive. So, numerator and denominator both are positive, and when it is mild slope means bed slope is also positive. We talk about negative bed slope only when we talk about adverse slope. Slope falling in the direction of flow we refer as positive slope. That we emphasize when we were doing derivation of the gradually varied flow, perhaps we remember that, and that is why this SB is also positive, and this means that dy dx, that is the change of y with respect to x. Say depth here is y, here is suppose y1, then change of y with respect to x, x is this direction, is positive, means it is a rising profile. So, this will always be positive. If it is negative, then only it will be a falling profile. Say this is y1 minus y. So, this suppose y1 minus y, if this distance is delta x, then this rate is y1 minus y divided by delta x. Like that also we can write if we want to discretize that. But anyway, this dy dx positive means it is a rising profile, and based on that, actually in the last class we got this statement that mild slope m n zone 1, the profile we get is m1, and this is a rising profile. Well, now let us go further into the characteristic of m1 profile, and what are the other things that we need to study. Well, now we have seen that it is a rising profile. So, if I draw this line, say this is normal depth line, okay, this is normal depth line NDL, well, and then it is a rising profile. So, it will be rising like this, and CDL line will be of course here, that we may not draw right now, but well, let it be here, and this is the bed. Now, as it is rising profile, means this profile, if we see on the upstream side, this will gradually fall, and to what extent it will come? It will be coming to the NDL line, that is at extreme upstream, starting of the gradually varied flow profile. We can call that this is the starting of the gradually varied flow profile, this point, this section, and from here suppose it is rising, but at upstream end, extreme upstream end, we are getting that y is equal to y n, that is normal depth and the depth of profile is equal. That is bound to be, because it is coming down like that. Now, if it is the situation, let us see what will happen at the upstream end. So, at upstream end of the gradually varied flow profile. So, what we are getting, that y is, of course, we should not say that y is exactly equal to y n, because if we say that y is exactly equal to y n normal depth, then it is a uniform flow. So, we can call that y tends to y n, y tends to y n, almost equal to y n. Now, if this is the situation, then what will happen to this equation? dy dx, what will happen to dy dx? It is equal to SB, then 1 minus y n by y whole cube divided by 1 minus y c by y whole cube. Now, in this part, as we can see that when y n and y are almost equal, then this ratio, when y tends to y n, this ratio become 1. This ratio will become 1 in the numerator, and that is why this numerator part, that is 1 minus 1. So, this will become 0, 1 minus 1, that will become 0. So, what we can write, and once this part becomes 0, whatever may be the other value, this part is of course positive as we could see, but whatever may be the value of SB, so these are not coming into question. So, what we are getting, that dy dx is equal to 0, dy dx is equal to 0. So, at upstream end we are getting that there is no change of y with respect to x, there is no change of y with respect to x, and we already got that in uniform flow itself y is not changing with x. So, it is meeting the point at the end, and just when it will gradually, suppose we are increasing the y value, the slope wise, dy dx is 0 here, and dy dx 0 means this gradually varied flow line will meet the normal depth line asymptotically. So, y tends to become yn asymptotically, that is we can say from this particular value, that is dy dx equal to 0. Well, so this is one characteristic of M1 profile, that at upstream end the depth rises very slowly, because the depth is, that is the gradually varied flow line is meeting the yn asymptotically. So, it will be increasing very slowly, and that is why the length of M1 profile is quite large, length of because it will take lot of time to meet the yn or the uniform flow depth. Well, then at downstream point what will happen? At downstream point, of course, this is it is rising like this, then to what extent it will keep on rising? In fact, when we get M1 profile, then it is above normal depth. So, normally the flow cannot rise or cannot go beyond the normal depth line, or it cannot exceed. So, there must be some obstruction like that, there must be some obstruction or barrier or something must be there which has caused the water to rise, So, it is rising like that, and then when it will cross this barrier, it will definitely fall on the downstream side. Of course, what will happen on downstream? Right now, we are not concerned about that, but we are concerned about what will be the case in the extreme right hand side. Right hand side means basically not right hand side, it is the downstream side, extreme downstream side. So, this section, this sort of obstruction or say artificial structures that are constructed in the river, or sometimes we can have some natural barrier also. We can sometimes have some natural barrier also like that. Sometimes we can have say rock outcrop which can restrict the flow zone, and that can also lead to this sort of situation or different sort of situation. Well, so whether it is natural or artificial, point is that that sort of structures or section we refer as control section. That means, at that section there is a definite relationship between the discharge and the depth. Well, we will be coming to that later when we will be discussing unsteady flow, then it will be more relevant discussing that part. But anyway, here also we will be discussing it briefly, and at this point, that means depth of control section we can call, here is the depth of control section. So, at the downstream point we will be getting y equal to say y control at the downstream point. Of course, when it is a series of profile, then that depth may be governed by what is happening at the downstream end. So, like that different other situations may come, but at upstream we are very much sure that it will be equal to yn, and it will be just tends to become yn asymptotically, and at downstream point the control section depth will be defining the depth of flow profile, and in between from here to here, the flow profile is a rising profile. This will be a rising profile and the shape of the profile, what will be the shape of the profile? That will be governed by the equation dy dx, this equation. Well, if it is other type of channel section, then we can go for the general governing equation of the open channel flow, gradually varied flow. And well, so then let us see what will happen to the M2 profile. Well, before that, when we are just getting at the upstream point, dy dx equal to 0 means y is not changing with x. Well, but this dy dx equal to 0 generally can give us a feeling that the profile is becoming horizontal, because dy dx represent the slopes, and when we say that dy dx is 0, that feelings may come to our mind that the profile is becoming horizontal, but that is not correct, because here our y, that is depth, we are measuring with respect to channel bottom, not with respect to a horizontal datum. We are not measuring with respect to a horizontal datum. So, when we are saying that dy dx is equal to 0, means depth with respect to channel bed is not changing, depth of flow is not changing, rather with the direction of x. So, it will become parallel to the bed, not horizontal, it will become parallel to the bed at upstream end. Okay. Then let us see what will happen to the M2 profile. In M2 profile, this condition remains same. Okay. In practical situation, when we can have M2 profile, that of course different conditions we can have, but this CDL and the NDL, normal defline NDL, this will be there. And suppose there is a drop, something like that, canal drop, and say water was flowing from this point, and then it can come, it will come down. Okay, whether it will come down, that we will just get from our mathematical expression, but right at this moment we can say M2 means it is something here, M2 means it is something here. So, say Yn is this depth, Yn, Yc is this depth, and then depth of flow y. Right now I am drawing it in the drawdown shape or in the downward direction, because I know that, otherwise we need to prove it mathematically. Okay. Well, that y, let this be the depth, and what the condition we are getting in M2 profile, the condition we are getting is that Yn is greater than y, that means this, because the profile will always be between Yn and Yc. So, y is bound to be less than Yn, but it is again greater than this y, depth y is always greater than Yc, because the lowest limit of the M2 profile is, or rather we can say the lowest limit of the zone 2 itself is the critical depth line. Well, so Yn is greater than y, and this is greater than critical depth Yc. Now, if we refer the same equation, that is dy dx is equal to Sb into 1 minus Yn by y whole cube divided by 1 minus Yc by y whole cube. Let us refer the same equation. Well, and here also as it is mild slope, so Sb is positive, Sb is less than Sc, but it is positive, it is positive. Well, now when if we see the numerator, then we can see that Yn is greater than y. So, this ratio Yn by y will be greater than 1, Yn by y will be greater than 1, and then cube of that will be, of course, when 1.17 to the power cube, it will be also greater than 1. So, this ratio is always greater than 1. Then 1 minus, you can concentrate on the slide, then 1 minus this ratio, which is greater than 1, will lead to negative value of the numerator. So, what we can say, that numerator become negative. And what about the denominator? That you can see that Yc is less than y, Yc is less than y. So, this part again become fraction, and cube of that fraction will always be a smaller than 1 term. So, that way 1 minus smaller than 1 will lead to some positive value. So, that way this ratio 1 is negative on the top numerator and this denominator is positive. So, negative by positive, and this Sb is positive as b is positive. That way dy dx we are getting that this is equal to negative, whatever may be the value, but this is equal to negative. So, dy dx negative means this implies that the profile is a falling profile. So, depth y is falling with respect to x, it is decreasing with respect to x. So, in the direction, x means the direction of flow definitely, and so with the direction of flow the depth is decreasing, and that is why this profile now I can draw more confidently that it is like this. Now, well, up to that much it is all right, that it is a falling profile, that is one characteristic we are getting of M2 profile. But then what will happen at the upstream end and what will happen at the downstream end? Now, let us see at upstream end. At upstream, as it is falling, means if we just go back like this, it is bound to meet the normal depth line yn. So, at upstream y is approximately equal to yn, and as we know that when y become approximately equal to yn, this ratio become 1 and our dy dx become equal to 0, that we have already discussed in the last case of M1 profile, where we could see that when y approach yn, when y approaches yn normal depth, then dy dx become 0, and dy dx 0, that means y tends to become yn asymptotically again. So, the profile this gives us the condition that y tends to become yn asymptotically. Okay. And so, the profile will be on the upstream side, it will be like that. This profile will be gradually going down and it will be meeting like that. It will be meeting the normal depth line like that. It is gradually going down. Now, whether, let us see, so upstream part is clear. Now, what will happen at downstream point? What will happen at downstream point? Whether the same situation will be there in the downstream, means whether this line is also meeting CDL asymptotically like that, or something else will happen there. But at downstream point, what will happen as it is coming down? So, y is approximately equal to yc. Well, why I am writing approximately? Because if I write y is equal to yc, means that is the critical depth, and then we are on the critical depth point, we are not on the gradually varied flow part. Here the flow should vary. Well, so I am writing y is approaching yc. Now, when y is approximately equal to yc, then you can see that yc by y, that is the ratio yc by y of the denominator is becoming 1, and then 1 cube is also equal to 1, then 1 minus 1, that is the denominator become 0, Now, whatever may be the numerator value will be definitely negative or whatever it is, but anything divided by 0, that become infinity. So, dy dx is equal to, we can write infinity. So, at downstream point when y is almost equal to yc, dy dx is infinity. Well, by that what we mean? That is change in y, dy dx is nothing but change in y due to small change in x is infinity. Means you just change it by small amount, your y change is very large. Means that can be possible only when this line is coming like that and it is meeting it perpendicularly, because with little change in x, y is changing to a very large value. That means when dy dx is infinity, we can say that the profile will meet the CDL line normally. Profile will meet the CDL line perpendicularly, well, normally. That is why the profile shape will be like this. On this part it is meeting asymptotically, it is coming smoothly, and here it is meeting perpendicularly. So, that is how we can define the characteristic of, say, M2 profile at downstream. So, this will indicate, this implies that y tends to become yc, or rather we can write the profile meet the CDL line, CDL, that is a critical depth line normally. Okay, perpendicularly it means. Perpendicular means this perpendicular is to the CDL line, not to the horizontal, because again CDL is parallel to the bed line. So, it is, with that respect we are saying that it is meeting perpendicularly. Okay. So, that way we are getting characteristic of M2 profile, and there are some other finer points here, because when it is meeting perpendicularly, then at that point when flow is occurring like this, of course what will happen in the downstream means after that it is entering into the zone, after that it is entering into the zone 3, or it may happen that when it is a fall, then it is coming like this and then it is meeting perpendicularly and then it is falling down on this part. So, this part we are not talking about, but we are talking about the profile what is happening here in the zone 2. But one important point I want to highlight here is that in the governing equation of gradually varied flow, we did make one assumption that hydrostatic pressure prevail. That means, pressure when we compute, then we are computing with respect to considering as if the flow is static, and that is true when the streamlines are parallel. When the streamlines are parallel, we can have it, but when it is meeting perpendicularly, the flow streamline will be having curvature, significant curvature at this point. So, when we compute the flow profile at this point, of course, this zone is very narrow, this zone is very small, because change in slope is infinite, means it is at a very fast rate it is changing. So, a small portion at the downstream end of the M2 profile, here the condition of hydrostatic pressure may not prevail, will not prevail rather, because of the curvature, and we may end up while computing we may end up with making some error at the point. Of course, this zone is so small that for practical purpose we can neglect that. Well, then let us see, we are left with one more profile in mild slope, that is M3 profile. Okay. Now, in M3 profile, say this is bed, slope is always mild, SB is less than SC, and of course, it is positive, and as explained already, this is CDL and this is NDL, this is NDL, and profile here is lying in this portion. And right now, I do not want to say that it is rising or falling, but it is a profile here, and then depth here is Y, critical depth line up to critical depth line it is YC, and depth here is say YM. Now, so what condition we are getting? That is YN is greater than YC and is greater than Y. So, Y is the smallest value here, depth of flow profile is the smallest one, and other values are bigger, that is normal depth and critical depth. Then going back to our equation again, say dy dx is equal to SB into 1 minus yn by y whole cube divided by 1 minus yc by y whole cube. Well, again if we see this equation, then we can see that yn is greater, in the numerator yn is greater than y. So, this fraction will be something greater than 1, cube is greater than 1. So, 1 minus something greater than 1 will be negative. So, this will be negative, okay. This will lead to negative value. And then in the denominator, this is also yc is this time again greater than y, unlike the M2 profile. Here yc is also greater than y. So, this value is also a this fraction, rather this ratio is greater than 1. So, 1 cube greater than 1 cube. So, 1 minus something greater than 1, that will also lead to negative value, and SV value is of course positive, because we are talking always about mild slope which is positive. Then this negative in the numerator, negative in the denominator, that will make the ratio, total ratio again positive, negative by negative. So, it is positive, SB is positive. So, what we are getting, the dy dx is positive. Now, when dy dx is positive, what it means? Again, this implies the profile is rising, profile is rising. So, we are getting again a rising profile. Now, so this will be a rising profile like this. Now, I can draw this shape as a rising profile, okay. Then what will happen at upstream and downstream? Again that question rise. In between, of course, in between the shape of the profile, we can determine from the governing equation by solving the governing equation, okay. But what will happen to the boundary value, boundary limit, that is at upstream and downstream? Let us see at downstream what will happen. First, let us see at downstream, because already we have done this. At downstream, y is approximately equal to yc, and when y is approximately equal to yc, that point we know that this value become 1, and then 1 minus I mean this ratio of the denominator, this become 1 yc by y, and then 1 minus something which is also equal to 1, then this become equal to 0, denominator become 0. So, when this becomes 0, the ratio dy by dx become infinity, dy by dx become infinity, okay. And of course, if we think about yn by y in this time, then yn is of course greater than 1, and this will become negative, and will be having some definite value, and SB is positive. But anyway, this is becoming ultimately minus infinity, or anything divided by 0, we can call this as a infinity. Our basic requirement is that what will be the shape of the profile. So, it is rising, negative means dy dx is rising like that, and at this point at this point it is meeting the CDL line normally. So, this implies that the profile meets CDL normally. So, that relation already we obtained. Well, that means on the downstream part it is clear that it will be meeting CDL normally. Now, what will happen to the upstream part? What will happen to the upstream part? That is, at upstream y, what will be the y? The depth of flow is coming down. So, as it is coming down, it appears that it will meet the bed, and when it is meeting the bed, the depth will become 0. Now, of course, for practical purpose, that upstream depth cannot become 0. Depth cannot become 0, because say 0 depth, from 0 depth it cannot start. If some discharge is coming, there must be some discharge, some depth must be, whatever may be the speed of flow, very high velocity, but if some discharge is coming, with very high velocity. Depth may be very small, but there must be some amount of depth. Practically it cannot become 0. But if we see the downstream shape, if we see the shape of the profile, and if we talk in terms of mathematical relation, then we can say that y approaches 0, y approaches 0. Now, if y becomes 0 or when y is approaching 0, we can now just mathematically see that in the equation you can see in the slide, that is y n by y, this is 0. So, this term become infinity, 1 minus infinity, again we can call this as a infinity, and then the lower terms, that is the denominator, this also become infinity because y is approaching 0. So, when our dy dx we can write as dy dx we can write as infinity by infinity. Now, infinity by infinity is mathematically we can say it is undefined. So, we cannot really have a very definite idea about the point what will happen, that just at the extreme upstream end. It will depend on basically the depth of flow here, and this will be coming from this particular depth, and this profile cannot go up to the 0 depth, that is what we can say, and it is undefined. So, if we want to draw something here, we can just put some dot here indicating that we are not sure what will happen if it is approaching 0. So, it is undefined. That is why we can put some dotted line, dot here indicating that this is undefined, and then this profile will be rising like that, and it is meeting the CDL line in this form, that is normally. Okay. So, that is what the characteristic of M2 M3 profile, and this is of course a rising profile. So, following this procedure we can analyze the characteristic of different type of profile. Now, let us see what will happen in case of S1 profile, that S1 profile. Till now we were discussing about M1, that is M2, M3, all are mild slope, and now we are going to the steep slope. Well, the S1 profile means it is a steep slope like this, and in case of steep slope this SB is greater than SC, critical slope, and of course positive, but it is greater than SC. And when it is greater than SC, then our normal depth line will be somewhere here, say NDL, and critical depth line will be above the normal depth line. This is what CDL. Now, when we talk about zone 1, that means the profile will be here, and so this is our Y. This depth is YN, and this is critical depth YC. Okay. And the condition that we are getting is that Y is greater than YC, and YC is greater than YN here. And then if we go back to our equation again, say dy dx is equal to SB, then 1 minus yn by y whole cube, 1 minus yc by y whole cube. Well, the same equation. Here we can see that as the profile is in zone 1, so y is greater than yn, means this ratio, that is the ratio of yn by y in the numerator, is a fraction, and that will be less than 1. So, 1 minus less than 1 will become positive, and in the denominator also the yc by y, that is also a fraction, and cube will be again a less than 1, and 1 minus something less than 1, that term will become positive, and SB is also positive. So, that way these are the terms we are having, and that way we are getting that dy dx is positive. Well, that means it is a rising profile, dy dx is positive. Now, if it is rising profile, then let us see at upstream end what will happen. Well, at upstream end, as we know, here CDL line is on the top, that is critical depth line is above the normal depth line. So, when the profile is coming down, it will be meeting the critical depth line, not the normal depth line in case of S1 profile. Well, so at upstream point, y is approximately equal to yc. So, when y is approximately equal to yc, then we can have, that is, this ratio yc by y will be equal to 1, and then 1 minus 1 will become 0, and that means again we are coming back to the original point. When y meet yc, then dy dx is becoming infinity, dy dx is becoming infinity. Okay. And when dy dx is becoming infinity, what it mean? That the profile, this implies the profile meet CDL normally. So, here the profile will be meeting the critical depth line normally, and it will be going like this, it will be meeting like this, and it is going like this. So, the shape of the profile at the upstream end, this will not go continuously extend to far distance by this way, and rather it will be just rising from the critical depth line in this way. Of course, this is just we are discussing about the characteristic of S1 profile, and in nature it is not that flow is coming in critical depth line and it is jumping like that. Basically, it will be coming in the normal depth line, always the normal flow will be occurring, or without any obstruction, without any barrier to the flow will always tend to move with normal depth line. So, it will be coming as a normal depth line. Then there must be something, some disturbances, maybe some obstruction like this, dam sort of things or anything, it can be some obstruction, and then the flow is rising, say flow is crossing this part. It may happen that flow is crossing this part and it is moving like this. Again, there will be some control section at the downstream, there will be some control section at the downstream, and before reaching or before starting of the S1 profile, there must be some flow profile here which will lead the flow to move from normal depth to the critical depth line. Of course, there may be some other combination what that we will be discussing when we will be discussing about the flow profile on series of channel slopes. Say if different channel slopes are changing, then how profile is occurring, that we will be discussing. There we will be discussing these things in more detail. But here, so for S1 profile is concerned, it will meet the CDL line normally, and then it is always rising like that. And at downstream, what will happen, that the depth will be y is equal to y control. So, this is a subcritical flow, and although it is on steep slope, do not take it like that, that if the flow is on steep slope, it is always supercritical. It is not like that. If it is flowing normally, uniform flow, then only it will be supercritical. But here the flow has somehow gone up to above the critical depth line. So, when here it is flowing, it is a subcritical flow, and this control section is here, and this will just govern what should be the depth of flow at the downstream point. Well, that we will be discussing in more detail in our later part. Well, but this downstream y is equal to y of the control section. Okay. So, that way we can say that characteristic of S1 profile, that it is a rising profile, it meets the CDL line normally at upstream point, and it rises till the control section is arrived. Okay. And of course, something else can be there on the downstream. Then let us discuss about the characteristic of S2 profile, characteristic of S2 profile. Here the bed slope SB is greater than SC, the same thing, this is normal depth line NDL, and this is critical depth line CDL, and our profile will be here. And okay, let me draw it as a falling because I know this. In fact, now we all can be confirmed about one point, that is when a flow profile is occurring in the zone 2, it will always be a falling profile, because from this equation it is very clear. And now whenever we get a flow profile in the zone 2, we can draw it as a drawdown profile, because this equation dy dx is equal to SB 1 minus yn by y whole cube 1 minus yc by y whole cube. From this equation it is clear that in zone 2 this normal depth, either of these things, I mean if it is in zone 2, if it is steep slope, then your critical depth is greater than y and normal depth is less than y. So, if one ratio is positive, then other ratio is negative. And if it is say mild profile, if it is mild slope profile, then your normal depth will be top, that is normal depth will be greater than the depth y, and critical depth will be less than the depth y. If critical depth is less than depth y, then this ratio will be fraction and this will be positive, denominator will be positive, but numerator will be negative. That means either numerator or denominator will be, if one is positive, other will be negative. So, ultimate expression for dy dx will always be negative, and that is why this profile is always a falling profile. Any profile in zone 2 will be a falling profile. Okay. So, now we can draw it very clearly. So, this indicate that we can write, well in this case our yc is in the denominator, yc is greater than y. So, this ratio is larger than 1, and so this 1 minus something larger than 1 greater than 1 will lead to negative, and this part is positive. On the numerator it is positive, this SB being positive. So, we can have the dy dx is negative finally, and this indicate that profile is falling. Profile is a falling profile. Fine. Then what will happen at upstream and what will happen at downstream? Once we do that, then only our analyzing or analysis on characteristic of S2 profile will be complete. Okay. So, let us see at upstream what happened at upstream. At upstream, y is approximately equal to yc, that is, it is meeting the yc. So, when y meet yc, that we have got several times, that when y meet yc, then dy dx is infinity. So, we need not explain it anymore, because we have this, we have discussed this issue. So, at y approaching yc means at upstream dy dx is equal to infinity. So, it indicate the profile meet CDL normally. And at downstream what will happen? At downstream y is, so okay, let me complete this part. This is say meeting normally means it will be coming like this, and then it is moving in the downstream side. So, what will happen at the downstream point? At downstream y is equal to yn. Then when y is equal to yn, then this part become 0, the numerator become 0, numerator of the equation expressing dy dx, that become 0. So, this indicate that dy dx is equal to 0, and mathematically saying dy dx equal to 0 physically means that the profile will meet the NDL asymptotically. Well, so what will happen here, this line will be meeting this normal depth line asymptotically. It will keep on going like that, and at a far distance it will be ultimately merging with the NDL, merging with the NDL. So, we can just see that this dy dx 0 means profile or we can write simply that is y tends to become yn asymptotically. Well, so this completes the shape of the S2 profile, shape of the S2 profile. Well, then it is going like that. Now, let us see what will be the characteristic of S3 profile. Well, in S3 profile, this slope is steep as well, and this is our NDL, this is CDL, and profile is somewhere here. Again, I am drawing it as a rising one, because now we can write with confidence that this is always rising if it is somewhere in zone 3. Well, this condition is YC is greater than YN and is greater than Y. So, referring to our equation, say dy dx equal to SB into 1 minus yn by y whole cube 1 minus yc by y whole cube. Well, then going to this equation, again here SB is greater than equal to SC, and this is positive. So, we can write as this is positive, and then yn by y, this you can see that normal depth is greater than y. So, this ratio will be in numerator, the ratio yn by y will be greater than 1. So, 1 minus something greater than 1 will be negative, and in denominator also yc is greater than y. So, it will also be negative, and finally, what we are getting that dy dx is positive, So, it is a rising profile, it is a rising profile. Well, so this rising profile, again if we extend it on the downstream side at boundary value, what will happen, that we need to know. So, whether it will be of this shape or it will be of something else, let me draw it. Okay. At downstream point, y tends to become yn, approximately equal to yn. So, we are discussing already, and we have discussed several times, then when y approaches yn, then dy dx become 0, and this physically means that y tends to become yn asymptotically. So, this statement indicate that the profile will be coming like this, and it will be meeting the normal depth line like that. Profile is meeting the normal depth line like that. It is asymptotically, not normally. It is coming like this, and it is coming in the upstream direction like that. And at upstream, what will happen? At upstream, again, if we see that y, if it approaches 0, if y approaches 0, then as per this expression, in the numerator also yn by y become infinity and 1 minus infinity. So, this is remaining as say minus infinity, and this part is also denominator also y is very large than yc. So, this is also infinity, and finally, what we can have that dy dx is equal to say minus infinity by minus infinity, it is basically infinity by infinity. So, this become again undefined. Well, so this become undefined means we cannot define this part properly. So, we should draw it like that, putting some dot here, then we are continuously extending. And in reality, this undefined means in reality we cannot have this situation, because at upstream point depth cannot become 0. So, we cannot have this situation. It will always be, there will be some amount of depth, and up to that depth we can always start computing, or we can always continue our computation up to that depth. And our depth computation of upstream depth will continue up to the depth where we have some definite depth at the upstream point. This case may be, suppose you have a sluice gate here and you are releasing the water, then it is going like this, and then it is rising like this sort of profile, and then our depth of computation will be up to the depth somewhere here. Okay. That part we will be discussing in more detail, of course, but so for characteristic is concerned, we can discuss the characteristic in this form. Well, so today in this class we have discussed our characteristic of mild slope profile and steep slope profile, and all the three profile M1, M2, M3 and S1, S2, S3. And we need to discuss about characteristic of C1 and C3 profile, A2 and A3 profile, and H2 and H3 profile. So, after discussing that characteristic, we will be discussing something more about the control section, and then after that only we will be going for computation of gradually varied flow. So, we will be taking up all these in the next class. Thank you very much.